We're going to discuss the parameterized surfaces. Why parameterized surfaces are important to us? So let's take a look at two visualizations here. For example, as you can see, the object, as t increases, start moving along this path. So your x and y depends on t. Or in this visualization, if you have, for example, UV plane, and your object is moving on the UV plane, if you can find a connection between UV and X and Y, you can easily connect the relation between moving this point on UV plane to XYZ surface. Especially it is important when we are calculating integrals. Sometimes using new parameters or reducing the number of parameters help you to do the calculation easier. In this example, we want to identify the surface with vector equation given to us as r of u and v, which are two parameters here, and it's defined as 2 cosine u in the direction of x-axis plus v in the direction of y-axis plus 2 sine u in the direction of z-axis. So what is the parametrization that comes to mind? What is this object look like? Remember that. First of all, this quantity here is 2 cosine u, and this quantity here is 2 sine u. From pre-calculus, remember that if you have sine squared of theta plus cosine squared of theta, the summation is equal to 1. At the same time, if you take 2 cosine u and 2 sine u and raise them to the second power, you can follow the formula of r squared sine squared of theta plus r squared cosine squared of theta, which indeed is r squared. Well, with the given information, if you take x to be 2 cosine u and take z to be 2 sine u, then raise these to the second power. X squared plus z squared, which can be written as 4 cosine squared of u plus 4 sine squared of u, it is indeed equals to 4. What about the middle term here? What does this guy represent? Well, v is nothing but y. Well, if we think about these two variables, u and v, and three variables, x, y, and z, this guy basically represents a cylinder in the space. This cylinder in the space is not like a vertical cylinder. It's a horizontal cylinder. As you can see, the axis is along y-axis. That's why v and y are equal to each other. And the base of the cylinder is located in XZ plane. So this is a parametrization for your cylinder. In the next example, suppose I ask you to find a parametrization for a cone. The cone given to us as z equals to square root of x squared plus y squared, and z is bounded between 0 and 1. Let x to be r cosine theta and y be r sine theta, and z is the same as itself. Again, remember that sine squared plus cosine squared is always 1. This is trig identity. And r squared sine squared plus r squared cosine squared is always r squared. Now, with this information, z is equal to square root of x squared plus y squared given in the question to us. If you plug those in, you get r back. So r squared cosine squared plus r squared sine squared inside the radical. Remember that this is nothing but r squared. The square root of r squared is equal to r. The visualization of this cone is located here. We know that z is bounded between 0 and 1. We have a range for our z, and z is a square root of x squared plus y squared, which is equal to r. Well, In this case, we can rewrite this cone equation as r of r and theta. R is the radius and theta is the angle, as your x's are cosine theta, your y is r sine theta, and z is equal to r. And r, which is equal to z, is bounded between 0 and 1. Theta ranges between 0 to 2 pi because you have a full rotation here. So now we're done with the parametrization of a cone. We're going to take a look at the parametrization of a sphere that you learned in triple integrals. Suppose I ask you to find a parametrization for the sphere centered at the origin with radius a. X squared plus y squared plus z squared is equal to a squared. Remember that in triple integral, we learn how to convert spherical coordinates into rectangular coordinates using x, y, z, rho, phi, and theta. X is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. You're going to use these and the ones that you learned before. And these are the parametrization that we're going to use for a sphere. So take x to be a sine phi cosine theta, y is a sine phi sine theta. Please note that instead of rho, we're using a fixed value a, and z is equal to a cosine phi. With this definition, you define two parameters. The very first parameter, which is phi, let us call it u, and the second parameter, which is theta, let us call it v. So the function connecting phi and theta, or u and v together, is defined as a sine phi cosine theta in the direction of x-axis plus a sine phi sine theta in the direction of y-axis, and your z is a cosine phi in the direction of z-axis. Remember that phi ranges between 0 and pi, and theta is in between 0 and 2 pi. So far we've defined some popular parametrization: sphere, cone, and cylinder. We're going to use this to define and calculate surface integrals.